Chapter 9.3, Modular Arithmetic. So this chapter is going to basically show us the intersection between our study of working in other bases with group theory. So first, let's look at modular versus clock arithmetic. These are very similar systems that are kind of easily confused. So a modulo, which is where modular comes from, a modulo M system consists of M elements, the numbers 0 through M minus 1, and a binary operation. Generally addition, but we can see it with other operations as well. So modulo 12 arithmetic. If you think back to the clock 12 arithmetic table that we looked at in the previous chapter, you'll see some similarities here and some very obvious differences. So there is one difference in notation between these. The main thing is that instead of having the number 12, we've replaced it with the number 0. So we've brought back our traditional 0 as the identity instead of 12. That's really the only difference. So this restructures the table a little bit, but otherwise it's still addition we can understand, but instead of having a 12 at the top of our clock, we now have a 0 at the top of our clock. So 1 plus 1 is still 2, but when we do 7 plus 5, instead of that being 12, it's now 0. So it loops back to 0 when we pass by 11. So our set of elements are 0 through 11 instead of 0 through 12, or instead of 1 through 12. And we can shorten this to mod 12 arithmetic instead of modular 12, but mod 12 arithmetic is traditionally with the addition. Otherwise, it's going to work the same way as the clock arithmetic we've already gone over. So just like with the clocks, we can also change this to be any number. Like we don't need it to be clock 12, we can make clock 8, or in this case, mod 7. So a mod 7 table, addition table, can be used to, for example, determine days of the week, where Sunday equals day 0, Monday is day 1, and so on. So if today is Thursday, what day will it be 6 days from now? Well, I have the table in front of me, but let's think about this on a clock. So if I draw my clock here, and I have 0, 1, 2, 3, 4, 5, 6, and I'm actually going to stop there. I gave myself room for 7, but we don't want 7, right? Because 0 is Sunday. So I actually have all 7 days here, right? So if I want to start on Thursday, well, so Sunday, Monday, Tuesday, Wednesday, Thursday, this is where I'm starting, and I want to know what happens 6 days from now. I go 1, 2, 3, 4, 5, 6, and I end on the third day. Well, what's the third day? Once again, Sunday, Monday, Tuesday, Wednesday. So we can see this reflected on the table, that when I look for Thursday, day 4, and add 6, I get 3, and that 3 is our 7. So we say 4 plus 6 equals 3 mod 7. This is how we mark that we're in modular 7 arithmetic. Similar to how when we did our calculations in other bases, we would write a little subscript 7 to say we were in base 7. Here we will write mod 7 to tell us we're in modular 7 arithmetic. So let's do a similar thing and ask, if today is Sunday, what day will it be 23 days from now? So on this table, I can't add 23 directly, right? But again, if I draw out my clocks, like so, then I can see, starting at Sunday, which is to say starting at 0, I want to go 23 around this, right? So let's see. That's once around is 7, 14, 21, and then 22, 23 is how we get to 2, day 2 being Tuesday. So, in other words, 0 being Sunday, plus 23 equals 23. We know this in normal addition, but 23 is 7 plus 7 plus 7 plus 7, plus 2 left over. So we say it is 2 in mod 7. Notice that this is actually the remainder when we divide 23 by 7. 23 divided by 7 is 3 with 2 left over. So, in fact, mods come from remainders. That's where this big relationship to our working in other bases is going to come from. So let's talk about congruence and modulo classes. So we say A is congruent to B mod M, written as A with, it's like a fancier equal sign. So it's got 3 lines now. So these 3 lines is the congruence symbol. So A is congruent to B mod M if A and B have the same remainder when divided by M. So in any modulo system, we can develop a set of modulo classes by placing all numbers with the same remainder together in the appropriate modulo class. So the solution to a problem in modular arithmetic, if it exists, will always be a number from 0 through m minus 1, where m is the modulus of the system. So in other words, again, if we go back here, 0 plus 23, yes, that's 23, but 23 is congruent to 2 in mod 7. So we can see this, the mod 7 classes reflected here. So if I look at 2, 23 is within that class. All of these, if I divided by 7, their remainder would be the number in the top row, right? 14 divided by 7, it divides evenly. It's perfect. 7 times 2 is 14. So it has no remainder, 0 remainder. Whereas 24 divided by 7 would get me 3 7s to get to 21, and then 3 left over. So I have 3 as my remainder. So that's what our modulo classes mean. So a question you could be asked is, what is 24 congruent to in mod 7? And our answer should always be one of these numbers. It's congruent to a lot of things, but specifically the one we want to look for is the number in that top row, which we just highlighted, which is 3. All right, let's try again now without the table in front of us. So what is 60 congruent to in modulo 7? So to find this answer without the table, we take 60 divided by 7 and look for the remainder. So how many 7s until we get to 60? Doesn't entirely matter, but we need to think this one out. So how many 7s until we get to 60? We've got, so 8 times 7 is 56, and then there's 4 left over until we get to 60. So we say the remainder is 4, so 60 is congruent to 4 mod 7. What about 25 in mod 12? So how many 12s until we get to 25? Well, 2 times 12 is 24. Then there is 1 left over to get to 25. So 25 is congruent to 1 mod 12 because 1 is the remainder when I divide 25 by 12. How about 412? Mod 4. Okay, so this one might be a little bit harder to do in our heads, but 412 divided by 4 on a calculator will tell us it's 103 evenly. So because this divides evenly, we say the remainder is 0 because 412 is just a multiple of 4. So 412 is equivalent to 0 mod 4. Now, what about if we want to start doing other operations? We've seen what a mod addition table looks like, but what about a mod subtraction? So if we want to determine the positive number replacement, that is less than the modulus, for the given question marks, how would we do that? So 3 minus 5 is congruent to what in mod 7? So again, we have multiple ways we can do this. We can create a table, or we can create a clock. Or we can replace these numbers with other things that are greater than it. We have a lot of options. So the option I'm going to highlight written out is first one where we notice that, well, 3 minus 5 would give us -2. So we want to essentially bring one of these numbers up a modular class. So instead of 3, I'm going to replace it with another number it is congruent to, that is just 1 up. So how do I get 1 up? Well, I think about what else would have a remainder of 3 when divided by 7. The easiest way to answer this question is just add 7 to 3. So 7 plus 3 is 10. So I can replace 3 with 10 because 10 is in the same modular class as 3 because 1, 7, and 3 left over. So the remainder is 3. So if I replace this with 10, then I can do the subtraction, right? So 3 minus 5 is equivalent to 10 minus 5. So that's congruent to just straight up 5, because 10 minus 5 is 5, and that's normal subtraction. We know how to do that. And so our answer is 5. But what if I wanted to do this in a more visual fashion? So I can draw a clock, right? And I will put my up to the mod, but not including the mod numbers, 1, 2, 3, 4, 5, and 6, no 7s. And now I start at 3, and I subtract 5. So subtracting just means moving counterclockwise. So 1, 2, 3, 4, 5. And here we are. So that's another way we can visually see what -2 is in mod 7. -2 just means counting back 2 from 0, essentially, or counting back 5 from 3. We can always visualize this on the clock, so that's a very helpful way of doing it if the replacement strategy doesn't make sense to you. Okay, let's try another one. So we want what -3 is congruent to 3 in mod 5. Well, let's think about this just normally. What -4 equals 3? Well, that would be 7, right? 7 minus 4 equals 3. But 7 is not less than the modulus, right? We want a number less than 5. So we're looking for what is 7 congruent to in mod 5. So that answer, we just need to think about what's left over when I divide by 5. So there's 1 5 and 2 left over. We can also get this through subtracting off 5s. So I subtract a 5, I get 2. That's really where this comes from, is if I can just count down by the modulus. So 7 minus 4 is the same thing as 2 minus 4, which is congruent to 3. So our answer is going to be 2 because we want to only include numbers less than the modulus. And again, why don't we draw a clock to visualize this? So we're in mod 5 now, so I'll put 0, 1, 2, 3, and 4 on here. And I want what -4 is congruent to 3. So we want to end here, but we have subtracted 4. So that means I'm coming from what direction? I'm coming like this way to subtract, right? So I want to count backwards by 4, which is forwards. It's kind of weird, I realize. But 1, 2, 3, 4. And so if I subtracted 4, I'd be here, right? So 2 minus 4 gets me 3 on this clock. There's several ways we can go about this, whatever makes the most sense to you. But I highly recommend sketching those clocks. Just make sure you have the right numbers on there, or else you will be very off on your answers. So, okay, last one. 5 minus what is congruent to 7 in mod 8? Okay, so, well, 5 minus what is congruent is equal to 7 normally. Unfortunately, it's going to be a negative number, right, normally, and we don't want to use that. So what can I do is I can bump the 5 up a congruence class to look at this. So if I bump it up a congruence class, that means I'm adding 8. So 5 plus 8 is 13. So now 13 minus what is 7? The 13 and 5 are in the same class, but it's just up a level. So they both, when I divide by 8, I get 5 as the remainder. So 13 minus what is 7? Well, that would be 6. So that's what I can do, but again, we can visualize this as putting it on a clock, right? 0, 1, 2, 3, 4, 5, 6, and 7 now, because we're in mod 8, we go up to 7. And I want to know 5 minus what gets me to 7. So how far until I get here? Well, that's 1, 2, 3, 4, 5, and 6. So again, we can visualize. All right, what about another operation we can do? So we've done addition, we've done subtraction. Let's try multiplication. So we're going to determine all positive number replacements that are less than the modulus for the given question mark that makes the statement true. So the interesting thing about multiplication is we can get more than one answer, actually. So a hint here is that we want to replace the question mark with each number under the modulus, then determine which multiples are actually in the class we want. So that's what we're going to do, is we'll start with mod 5, and we'll replace this question mark with 0, 1, 2, 3, and 4. And we will see which one is actually true. So 2 times 0 is 0. 0 is equivalent to 0, mod 5. 2 times 2 is 4. So that's still 4, because again, the options of numbers are 0, 1, 2, 3, or 4. 2 times 4 is 8. Now here we actually have to bump it down as a modulo class. So 8 is equivalent to 3 in mod 5, because 8 minus 5 is 3, or we can say that to get to 8, we take 1, 5, and 3 left over. So our remainder is 3. All right, 2 times 1 is 2, so that just stays the same. 2 times 3 is 6. So that one, again, we need to find what it's congruent to. So 6 is congruent to 1 because it's 1 past 5. So which one actually works? Which one actually fills this in properly? It's going to be the 4, right? 2 times 4 gave me 3 like I wanted. So my answer is 4. So we only got one answer for that one. Oh, sorry, we just did that. Let's try another one. 3 times what is 0 mod 6? So I'm going to go through and do the same process again. So I plug in 0, 1, 2, 3, 4, 5. So 3 times 0 is 0. 3 times 2 is 6, which is 0 in mod 6. 3 times 4 is 12, which is also 0 in mod 6 because it divides evenly by 6. 3 times 1 is 3, so that just stays as 3. 3 times 3 is 9, which is 3 in mod 6 because 1 6 and 3 left over. 3 times 5 is 15, which is 2 6s and 3 left over, so it is also 3. So our answer here, we actually do get 3 answers. There are 3 times where we got a 0 out of it. So our answer is 0, 2, or 4. Okay. And our last one is going to be 3 times what is 2 in mod 6. So I've got the same chart, right? Same chart, but now I want to know when is it 2, and we can see that in fact, given these options, there is no way for it to become 2. It's either going to be 0 or 3. So in this case, there is no solution. So there's going to be times where we get multiple solutions, one solution, or no solution at all. That's entirely possible. So you may be wondering, we've gone through addition, subtraction, and multiplication now. What about division? Well, for modular classes, we don't talk about division. So those are the only 3 operations we're really going to talk about in this class. But the last thing we want to explore is the concept of our modular arithmetic as a group. So here I have the mod 4 addition table and the mod 9 addition table. And I can actually make this statement that all modular arithmetic systems are commutative groups under addition. We can see this visually. We've got closure. All these numbers are just 0 through 3, just 0 through 8. So we've got closure. Our identity is 0. It's always the additive identity when we're working with normal addition with zeros in it. We've got inverses. There's always a way to get back to 0. We've got associativity because, again, it is just addition, even though there's some extra funkiness to it. And it has commutativity because of that main diagonal, like so. I didn't draw that very well, but again, it's there down the actual center. There we go. So we can see that symmetry across the diagonal that we like. But when it comes to multiplication, we do run into issues because we don't have inverses for 0. So that's why we only talk about the addition as a group.